Hi, my name is Lisa Richter. I'm Director of Industry Outreach and Growth for CSIA. Welcome to the Masterclass. Before we get started, a quick word about CSIA. Probably most of you here today are familiar with the association, but if you're not, all you really need to know is that CSIA's mission is to help system integrators build better businesses. How do we do that? Well, for starters, we have a team of volunteer SIs who have crowdsourced a best practices manual to help SIs scale their businesses. In fact, the BP committee just released a beta version of the latest manual 6.1. CSIA also offers a certification program and other resources, including professional development, learning from peers, and access to vetted professional service companies, including insurance and legal, who understand an SI's unique business needs. For partner members, CSIA offers an ecosystem to grow your SI programs, understand your customers' pain points, monitor industry trends, and share your thought leadership. With thousands of qualified integrators and suppliers, the CSIA Industrial Automation Exchange helps system integrators, industry suppliers, and manufacturers connect and do business. For system integrators and partners, it provides a platform to support your content and SEO marketing efforts, position yourself as a thought leader, and nurture prospects during their complicated buyer's journey. If you are not currently a member, now is a great time to join. Membership provides you and your entire team a full lineup of virtual events and other resources from accounting to sales to operations 365 days per year. It also means you and your team can attend the CSIA conference because this annual in-person event is members only. If you are currently a member, thank you. If you just want to get a flavor of CSIA and its members, I encourage you to listen to the Talking Industrial Automation podcast. CSIA members talk all things industrial automation, and it's just a great way to hear what your peers are up to. One last housekeeping note before I turn it over to today's speaker. If you have any questions during the presentation, please use the Q&A feature in Zoom. That just helps us stay organized. The session is being recorded and you will get a link to the recording in the next day or so. At this time, I would like to turn it over to today's speaker. Craig, take it away.
Thanks, Lisa. Hi, everyone. Let me take a second here and share my screen. My name is Craig Nikoloff. I am the product manager for the OEM product line for Mettler Toledo's North American Sales and Marketing Organization. A bit of background for me, I'll share here. I have been in the weighing industry for about 13 years now, from areas from vehicle weighing to dynamic weighing, and now currently within our OEM product line. So today we are going to talk about the proper weighing specification of measurement sensors in order to provide more value to end users and to simplify integration. So let's go ahead and get started. So a bit of an overview. I'm at Toledo. Hey, we are the largest precision measurement company in the world. So we've got 16 global manufacturing and distribution sites spread actually fairly evenly around the world. It's hard to see those green dots on the right side, but it's all basically roughly divided into thirds between the Americas, Europe, and Asia Pacific. We've got over 8,000 sales and service personnel and 16,000 total employees around the world. Again, 40 countries on service and over 100 others. So we've got this service organization spread out so that is very easily accessible to most companies around the world. And then finally, we are the number 26 automation company in the world. You wouldn't necessarily think that maybe from precision measurement, but we've developed some products that interface in a very friendly way with a lot of automation products out there, whether it be Rockwell or EtherCAT or Siemens and whatnot. But we'll get into a little more of that later. Today, we are going to talk about our industrial weighing solutions and ways to specify components for that. One more, I guess, just overview slide. You can see our global reach here. Blue and the green dots. The green dots are kind of hard to see, but they basically represent our sales facilities, sales and marketing facilities, as well as our manufacturing facilities globally. So bit of a look at the portfolio that I'm talking about. Hey, we've got solutions for every application in weighing, whether it be from 1 microgram all the way up to 1 million kilograms. The demonstration of various product lines, or APW product line, top left, bench portable and floor scales in the middle there, the platform scales, and then our weigh modules down at the end. And it varies whether it be analog to smart sensors. But that's just to give an idea of components that you would be encountering when we're trying to specify sensors for your weighing applications. So first, we're going to take a look at the methodology for scale selection. It's important to note that a capacity-based scale selection doesn't exactly account for accuracy. So we're going to look at 4 examples here, with the basis being, hey, we're weighing 1 kilogram of fine Swiss gold. And the cost per gram, at least at the time of creating this slide, the cost per gram was $75.57. So again, we're looking at 1 kilogram, not 1 gram, but the cost per gram is $75.57. So first, hey, if you're looking at a 3 kilogram balance, this 3 kilogram balance would have a stated, this particular one would have a stated accuracy of, let's say, 0.5 grams. So if you're looking at the variability based on the accuracy that can weigh at, there can be a variability of plus or minus $37.79. Again, half a gram, the cost per gram was $75.57. Next, moving on to a 30 kilogram bench scale. Hey, the stated accuracy there in this particular case is 1 gram. So that variability, again, with that accuracy of 1 gram, that variability is plus or minus $75.57. Moving on, hey, let's look at a 150 kilogram budget floor scale with a stated accuracy of 0.1 kilograms, so 100 grams. That's a variability of plus or minus $7,557. So notice that we moved up in capacity here as we were looking at these, but hey, let's take a look. Hey, at a 150 kilogram floor scale, it actually has a measurement uncertainty, a stated accuracy of 0.2 grams in this case. 0.2 grams at that cost per gram is plus or minus $15.11. So that accuracy matters when you're trying to specify a solution based on what you're looking for. Because again, as we're looking at the 3 kilogram scale in that first example with that half gram variability there, or accuracy, plus or minus $37.79, we're less than half that at a 0.2 gram accuracy. So measurement uncertainty is stated there. We're going to get a little more into that as we go further into the presentation. So measurement uncertainty. Hey, accuracy is relative to the process tolerance. So close enough equates to accuracy. It depends on the user's needs, and it has nothing to do with level of detail or digits beyond the decimal. So we've established that no measurement is exact because, hey, you've got that uncertainty no matter what sort of measurement you're taking. So there's some level of uncertainty in any number that we see. User has to decide how much uncertainty in that number is acceptable before it becomes an unusable measurement. Okay, so they have to determine what they want to be usable, and outside of those bounds, hey, it's an unusable measurement. So that's called a process tolerance. Accuracy is the condition in which a measurement has less uncertainty than the process tolerance permits. So exceeding it makes the measurement inaccurate. And we'll take a look at that here with this example. So what we're looking at here, 100 kilograms of this product, this red powder. With a measurement uncertainty of 0.5%, that translates into, so again, 0.5%, that actually translates into 0.5 kilograms here in this case. So you can be plus or minus half a kilogram and have 99.5 kilograms at the low end up to 100.49 kilograms at the high end. That's with a measurement uncertainty of 0.5%. So let's say that, hey, the process tolerance was designated as plus or minus 1%. So you're able to take in measurements, you're accepting measurements within plus or minus 1%. So from 99 kilograms at the low end to 101 kilograms at the high end. Note that that measurement uncertainty that we've noted up there in the blue is smaller than that process tolerance, than the acceptable process tolerance. So, hey, we would count this as an accurate weighment. Now, if you want to take that and you flip it, and your process tolerance is 0.5%, but then the measurement uncertainty of the scale that you've selected is actually 1%, that measurement uncertainty is larger, wider than that process tolerance. So this application then would be identified as an inaccurate application. Again, we just switched those two just to show you, hey, the relationship between process tolerance and measurement uncertainty. We always want that process tolerance to be larger than the measurement uncertainty. And we'll get into how to identify those as we move along. So quick note here, hey, Mettler Toledo, as a company, we define measurement uncertainty for weighing components and configured systems in a report and a methodology that we refer to as GWP, good weighing practices. But we're just going to speak generically about the approach to go into something like this as we move along in the presentation. So you just need to define the accuracy requirements. So things to think about: the criticality of your application. Are your measurements incredibly important? Is there a high risk to them in that, hey, you're measuring, let's say, multiple materials in a vessel? There's high cost materials. Like, what happens if you have to scrap a batch or something? Is it a massive hit to the bottom line of the company? Or is it just something that's been planned for and the material isn't all that expensive? The or then falls into the low risk measurements here. So low risk measurements, hey, if you're just quantifying inventory, you want to make sure you know how much is in the tank. You're not necessarily selling out of that tank. Or maybe you're dosing and filling into intermediary vessels. So it's not dosing into a final product. You're just trying to make sure you have an understanding of what you're dealing with before you get into something a little more precise. Or as I mentioned, hey, you might have low cost materials as well. So whether it's a high risk measurement or a low risk measurement, that feeds into helping you define how critical this part of the weighing process is for you. And that can then translate into identifying types of components and how accurate you would need to get in those weighments. So next, we talked about criticality. We'll talk about identifying acceptable error now. So whenever you're considering a process, and if there's, say, multiple ingredients involved in a process, you always want to use the tightest tolerance as the process tolerance. So in this example, where you're looking at a few ingredients: flour, sugar, salt, butter. The tolerance is there. You could say, hey, yeah, we're willing to accept a tolerance of plus or minus 12.5 kilograms of flour, plus or minus 5 kilograms sugar, 2.5 kilograms salt, and half a kilogram of butter. So it would seem, hey, that half a kilogram, that seems to be the tightest tolerance. It is the tightest tolerance. Now you see the weights there on the side, or in the middle rather. Those weights will help us to understand a percentage that we need to account for in terms of a process tolerance. We'll take a look at that here. So those translate then into a tightest tolerance of 0.5%. Now the math is easy because, as we saw, hey, 0.5 kilograms is what we're dealing with. The weight of that butter is 100 kilograms. So we're able to accept plus or minus 0.5 kilograms translates into 0.5%. So with that, hey, that has that tightest tolerance. So that should be used for the entire scale. We don't want to accept any tolerances larger than that, because outside of that tolerance, it would be an inaccurate measurement, at least for the butter. So also the lowest weight there is 100 kilograms that we need to measure of anything. So this is just a note for the future. Butter's also the net minimum weight. So we will be using that in specification later on as we help to identify this application. So just something to keep in mind. But main point in this particular slide is, hey, we're looking at a 0.5% process tolerance for the entire process. Next, we need to account for safety factors. So what are safety factors? Well, it's basically a sort of general number that you're using to identify how how much you're willing to accept in terms of, well, slop's the wrong word, but how much you're willing to accept in variability in the process, how it affects it, criticality plays into it, a number of things play into it, and we'll talk about that here shortly. So, one, several factors affect that tank scale accuracy. One is the dead load. The dead load accounts for, hey, the piping, the attached devices, mixers, blenders, other sensors, anything that would add weight to what you're trying to measure. Also, the support structure. The support structure, hey, maybe that's underneath the sensors, the weigh modules that you might be putting in there. Maybe it's over top of that. Either way, you need to account for that in terms of either dead load or in terms of how that can be affected by other external influences. And when we're talking about other external influences, hey, we're looking at, hey, fill cycle time. How long does it take to fill and empty that vessel? What are the physical effects on that while that filling is happening? Temperature. Hey, mechanical devices are generally always affected by temperature in some form, depending on how wide of a variability there is in that temperature. But hey, metal, it expands, it contracts, expands with heat, contracts with cold. What sort of environmental factors, environmental temperature factors could those components be seeing? Vibration. Vibration can be caused by any number of different things. It can be caused by the mixers, the blenders. It can be caused by seismic activity. Maybe you're in an area with lots of earthquakes, and that happens during the processes. Maybe there are lots of small earthquakes. Either way, that's going to be shaking the facility. That's going to be affecting anything in there mechanically. Some places may compensate for that by maybe having different foundations depending on the criticality of the process that's involved, not tying that in with the rest of the building so it's not affected by fork trucks driving over and those sorts of things. But either way, it's just something to think about in terms of an external influence. And then finally, hey, dirt and debris. Dirt and debris, I mean, we see this everywhere. I mean, people even will detail underneath their hoods just to make sure that things are clean, nothing influences things. In the case of weighing, hey, we've got the support structure here. Does dirt and debris fill in to the gaps to the point where certain things may bind? It may cause a mechanical interference, or it might cause additional weight depending on how much actually builds up on there. So main point here, hey, the safety factors, we want to plan for those external impacts on accuracy. So a bit of a real world look at a safety factor per se. We're factoring in sort of a comfort level. And here we're going to take a look at a car. A car has a stop, in this particular case, a car has a stopping distance tolerance of 112 feet. Do you trust that? Do you want to account for everything to be working perfectly without any sort of influences from the outside? Probably not. It's probably safer as you're driving along to say, add in, hey, another 56 feet, we'll say, as an example. So that comfort level that you've put into place, that safer following distance to add to that braking distance, hey, in total, we're looking at 168 feet in this example. You're doing that because you're trying to account for external influences like weather. Is the road slippery? Is there a phone involved in the situation? Did you get an alert and you're looking over at your phone and, oh no, I looked up and now I have less than 112 feet to stop? Are you messing with the radio or changing channels? And then also, hey, are you in a hurry? Just stress factors that could be affecting things as you're driving. You want to plan for additional safety in your process, in this particular case, in your stopping distance, because, hey, I recognize that a lot of stuff is going on. So when we're defining safety factors, they are just, it's just a number that we use as a multiplier in the particular, in the calculations to account for those influences. So a safety factor of 1 in an industrial environment, that would be essentially sort of a clean room with no external influences. I mentioned like separate foundations for things so that it's not affected by everything else going out in the facility. That's an almost near perfect sort of scenario, safety factor of 1. What we see in general industrial environments and what we recommend is, hey, utilizing safety factors of 2 to 3. Closer to 3 is even better. This will help us to, again, when we're factoring in the effects of accuracy, if we can identify components that are above what these safety factors end up specifying, then we found that we've identified measurement sensors that are fit for our purpose, fit for our application. So 2 to 3, I mentioned 3 here. We're showing in green. That's risky scale on the left, all the way up to the safest. All depends on your comfort level and how you want to address your application. So at this stage in the design process, we've identified what measurement uncertainty is. 2, identified the process tolerance and the relationship between the process tolerance and the measurement uncertainty. Again, we want that measurement uncertainty to be smaller than the process tolerance, which is determined, the process tolerance is determined by the end user, by engineers, based on everything else that we're dealing with, based on acceptable weighments. And then 3, that safety factor, depending on the criticality of the process and how these external influences may be affecting things, that is used as a multiplier to help us identify a fit for purpose application. So next step, you want to specify that weighing equipment that will meet those accuracy requirements that you've determined based on those first 3 things that we looked at already: measurement uncertainty, process tolerance, and safety factor. So the concept here for a weighing component selector. You are taking your application requirements as determined by the end user through your expert, and we are essentially taking a database of components. In this case, we've got load cells, weigh modules, the junction boxes tie the weigh modules together, and then terminals to be able to visualize that weighment, to see that, whether that be visually or seeing that within your automation system. A provider should be able to offer something to be able to help you address that in fit for purpose application. So next, hey, the requirements should be input by the users of this weighing component selector. So those application requirements are fed in, suitable components are established based on all of those process requirements that we've looked at before. And then finally, we identify those components and kicks out a report to help you understand what you're looking at, to help you understand that your application has certain factors feeding into it, and then the components that could work for your application. So we'll take a look here at a weighing component selector interface. 9 simple pieces of information to help us determine fit for purpose. The scale type, compression or tension. Is it hanging from a mezzanine? Is it being compressed? Are they weigh modules underneath all the mechanical components? The total capacity of the application. This includes both the material, the maximum capacity of the material that you're weighing, as well as the dead load, all of that equipment that we talked about before when we were talking about safety factors and whatnot. We've got dead load there, the vessel at number 4. Hey, the readability, the scale readability, we talked about that already. It feeds into tolerance as well, and helps you to identify the appropriate equipment if to be able to see the measurement properly. Number of sensors, of course, how many legs you may have under a tank, let's say. The load to be weighed, we talked earlier about that minimum net weight, that is something that we need to be able to see. We need to understand how accurate we can weigh at that minimum. If everything is almost essentially been fleshed out, we still need to know how much is in there. The maximum, of course, we don't want to put too much material into a tank that could overload the weighing equipment because of that. And then, hey, intermediate points, any critical points in between that you may want to be able to see during your processes. Process tolerances we've already identified. The safety factor, again, based on your comfort level and what you've seen, those external factors and the criticality of the application. That'll get factored into here as well. And then finally, hey, you can account for those environmental requirements as well. Again, those helped you understand the safety factor and how you needed to address it. So next, in the report, hey, after those inputs are entered, the GWP software, for in our case for Mettler Toledo, it creates that report detailing the weighing system. So just any report that will take in those factors, identify the components. It is great to have on hand, great to have for record keeping purposes, great to have for historicity, I guess, for historical purposes, so that you know, hey, has my application changed over time? What was it in the first place? I can go back and look at this documentation to understand, yeah, this is what we specified when initially identifying this information. So with that, hey, it's important to have that contact information, the name and whatnot. It helps you understand what you're looking at, which scale it might have been. Maybe you've got numbers of tanks and you've identified, hey, what application was this? What tank was this? What is this tank number 6 in the facility? This is the report that we're looking at here. Then the summary of the application. We already looked at that, somewhat talked about those factors that feed into it. And then the report should also kick out an orderable part number. So as an end user, you can look back at these reports and say, hey, this is what I'm looking at. You may not then have to go out to the facility to see if you can find a part number on the equipment. Maybe it's buried in such a way because of the installation and other things are built up around it. It's hard to see this report. You should be able to check back and look at an orderable part number and see what you need to obtain for the future. The report as well, hey, it's proof that those components are fit for purpose. So it compares that overall system uncertainty to the process tolerance, as we talked about before. So the proof of the suitability to maximum and minimum load, absolute measurement uncertainty for each load. You can see that specified next to there. Hey, the weighing tolerance. Hey, what can we accept? We specified that already. It's laid out formally. What the scale provides, what those components we've identified, how they will perform. And of course, we want to make sure that that uncertainty is smaller than that weighing tolerance. So in this case, hey, we see 0.02%, 0.04%, 0.13% at those various loads to be weighed. And the weighing tolerance that we've identified in this application was 1%. All of those relative uncertainty calculations are under that 1%. So ideally, this should say that it's fit for purpose, and it does. These green lights here, green logos, circles, are helping to identify that we're taking a look at that we're looking at components that are fit for purpose at those various loads to be weighed. And we're considering the safety factors as well, and we see the safety factor there noted. Hey, we talked about safety factors of 2 to 3 are generally pretty good for industrial environments. Depending on the criticality of your application, you can go even higher. You could see here, hey, the components identified here, hey, there's a safety factor. These account for an application that would need a safety factor of 51.2. And so is that larger than the safety factor that we've identified? Yes, absolutely. It's all very good. And then you'll see a note here at the bottom, the typical minimum weight for, let's say, a 1% weighing tolerance, as we've specified here in a safety factor of 2, is 52.82 kilograms. So that's well below any of those loads to be weighed as well. So also, the report should be able to compare multiple options for you to basically help you re-specify if any budget changes or whatnot. In this case, we're representing 3 different solutions from Mettler Toledo's weighing module portfolio. You can see the differing safety factors, 3.31 up to 3.84, depending on what we're looking at. It should allow you to compare side by side how that component should perform based on the capacity that we're looking at. And also, hey, as you're taking into account those options, there's other things to look at. A trusted advisor should be able to help you identify, hey, does this fit my application? Do I need the industry standard? Do I need something that's higher accuracy, whatnot? Does my application have any sort of external factors that influence things in such a way that it could be overloaded from the side? These are just things to consider as we're looking at and comparing different materials. Hey, in this case, the SWB 605 here, hey, provide sensor level data. Is that needed in your application? These are just things, again, that your trusted advisor would walk you through as you're helping to understand if your application, if the components are fit for purpose for your application. So then in the end, hey, it's a good representation of what you're looking at when it comes to a report to help you identify those components fit for purpose for your application. So next, hey, another thing to look at is connectivity in our Industry 4.0 world. Connectivity to all sensors, control systems, and IT platforms is now a must. And in our case, hey, we have our IND 360, our automation transmitter that can speak to the tank scales and silos, the bench and floor scales, integrated weighing components, automated precision weighing portfolio there on the right. Should be able to speak in via various automation protocols, EtherCAT, Profinet, Ethernet IP. These all come from various vendors, whether that be from EtherCAT, whether that be from Siemens, whether that be from Allen Bradley. And then OPC UA and REST API when it comes to IT systems and being able to translate that into those. So that connectivity is key, whether you're talking to operational technology systems, so systems out on the shop floor, or IT systems. So up in the office with your IT department handling things, if you're feeding that information from production all the way up to be able to account for that from a reporting perspective. Should be able to leverage easy integration to reduce your setup effort. Hey, standard connectivity, hey, with say that IND 360, they connect to weighing sensors in the same way every time, reducing system complexity. Should be able to have an ease of integration when it comes to PLCs with having AOPs, add-on profiles, add-on instructions on hand, sample code that will make startup easy, that will allow a controls systems engineer to take that code, plug it into, let's say, Studio 5000. In our case, we've got that already created, already certified via ODVA, and it just helps things to be a little more plug and play when it comes to integrating in an automation system. And then web servers. Hey, web servers are great from a remote access perspective. Helps you to either set up in person with a laptop on hand, if you wanted to, say, bypass a display, or if you don't have a display, that web server is very much key. And a restore and backup feature also will help to clone in the case of multiple installations. So if, say, you've got one transmitter already installed and you've got 10 more that you need to install, you can use the backup and restore function to install each subsequent component, subsequent transmitter. Fast integration into major automation systems, hey, it reduces headaches. So are you able to integrate, because of those add-on profiles, add-on instructions, GSD files, into the various automation protocols that are out there? So we mentioned already Ethernet IP via Rockwell, Profibus and Profinet for Siemens installations, EtherCAT for Beckhoff installations, Mitsubishi, same thing. Well, not the same thing as Beckhoff, but yes, also we can account for Mitsubishi. So then again, just looking at Mettler Toledo, hey, we've got our industry partners that we've worked with around the world: Rockwell Automation, Siemens, other software partners. Hey, and in this case, CSIA. Hey, thank you guys for letting us present on this webinar. It's a great opportunity. Other companies we might work with, subcontractors and partners, especially in the OEM world. We're working with OEMs, tank fabricators, machine builders, systems integrators. These are all those intermediate providers that are ultimately helping an end user install these installations. And having all that information on hand, those add-on profiles, having proof of fit for purpose from a weighing component selector, this is all very valuable information to be able to prove, let's say, to an end customer that the components utilized are fit for purpose and suitable for your application. And then, hey, with Mettler Toledo, as I mentioned already, we've got the global resources, the service organizations around the world that can help out when needed, when problems are encountered. We mentioned already, hey, it's good to have those plug and play for all major control systems. Those partners, those industry partners, and communicating with them to make sure that all our information is up to date. And finally, hey, what are you working on? How can we help? Again, my name's Craig Nikoloff. My contact information is here. Again, I am the product manager for the OEM product line for the North American Sales and Marketing Organization for Mettler Toledo. And I guess with that, that's what I have. I'm not sure if there have been any questions or anything. I don't know if you can comment on that, Lisa. But with that, I'd say thank you.
Craig, no questions, I don't think. Last call. Anybody here want to pipe up with a question? If not, then I will ask my colleague Karina to put up my last slides. On behalf of CSIA, I would like to thank our speaker, Craig, for this informative discussion, and also to thank Mettler Toledo for sponsoring this event. And of course, thank you for attending. Be sure to bookmark the CSIA events calendar so you don't miss any upcoming events. And that's a wrap. Once again, thanks for joining us and have a great day.
Thanks, everyone.